Hey, Vlad here, devinsidey.com. In the previous video, we learned about the ordering type class, and today we're going to see how absolutely not straightforward it is to integrate it into our collections library. Let's do this. As always, we're in the Ubuntu virtual machine and we're using Sublime Text, the editor of my choosing, which is fully maximized with a wonderful plugin called Terminus, which we're going to use to emulate the entire terminal for us, where we're going to run SBT inside of it and rerun the test every time we save the file. Before we even begin discussing today's topic, I want to mention that everything that we're going to do today, we're going to commit to a completely different branch, and in the next video of the series, we're going to go back to master and pretend like all the changes never happened. We did the same thing for the red black tree. In fact, if I go to git branch, it will show me that we have master and we have the red black tree. So what I'm going to do now is I'm going to check out -b. So this is going to check out the branch that doesn't even exist yet. -b is going to create it. We're going to call it ordering like this. So if I do git branch again, we're going to see, okay, now we're at ordering, and because I'm using the ZSH, it actually shows it in the shell prompt over here. Okay, so I'm just going to start SBT now over here, and I'm just going to rerun the tests and use the continuous running of the tests. All right, so let's do this. Okay. Should be already compiled, so it should be real quick. There we go, everything is green. Right, so what are we doing today? Well, today we're going to realize that our sats and our maps are actually hash sats and hash maps, and they're being backed by hash trees, which means that if I go to tree over here and I'm go to the add method, we're going to see that based on the hash code, the decision is being made whether the element should be put into the left side of the tree or into the right side of the tree. So today what we're going to do is we're going to inject an ordering into our trees, and we're going to let the ordering decide whether the element should be put on the left side of the tree or on the right side of the tree. Now, what could possibly go wrong with that? My original idea for this video was to start hacking at a solution and then arrive at a dead end and then backtrack from that, as I sometimes do, as you might already know by now. But the problem is that our homegrown collections library is not a baby anymore. So with every new video, I get to shuffle more and more code. So this is not viable for today. So what we'll do instead is the following. First, we're going to create a copy of our trees. We're going to copy the entire file. Then we're going to try to make our changes, and we're going to see that it doesn't actually go anywhere. So we're going to try to add ordering to our trees. So then once we realize that this is a dead end, we're going to comment it out. Then we're going to do a gigantic refactoring in the entire collections library. Then we're going to go back, comment it back in, massage it a little until it actually has our changes, and only then integrate it with the rest of the library, and then realize again that we have issues, and then we'll just stop. Okay, so the first thing that we do is just going to mark everything over here. I'm just going to create a new file. I'm going to paste it in. I'm going to save it as tree copy. Like this. Okay, it's not going to compile because it's going to say, hey, you have tree 2 times now. So I'm just going to go over here. I'm going to mark everywhere where it says tree, and I'm going to call it tree copy. So now everything should be green again. All right, so the first thing that we're going to do is we're going to realize that the only possible injection point for the ordering is the moment of creation of the tree, because if we allow our users to change the ordering every time they call contains or add or remove, we won't be able to ensure that this ordering that they inject is the same or it behaves the same. In fact, the topic that we're discussing today is extremely interesting, especially when it comes to discussions about type class coherence. In fact, we're going to avoid implicits as much as possible, at least in the beginning of this video. I will include a link down in the description about a very long Haskell video by Kmett where he talks about this topic. In fact, he also mentions Scala quite a bit, and in fact, he uses a very similar example at some point. All right, so let's start hacking. As I said, the first solution is going to fail, and usually I save the file quite frequently and rerun the test, but today I'm going to try not to, and in case I mess up and accidentally save, I don't want the test to rerun, so I'm just going to press enter over here. And also I'm going to collapse the sidebar so that we have more space. So the first thing that we're going to do is we're going to pretend that we already injected the ordering into the trees. In fact, let me close the other tabs, okay? So we're going to pretend that the trees, the tree copy, that it already has an ordering, right? So somewhere over here, let's say that it's over here, we're just going to have a def ordering of element like this, okay? And as we've seen in the previous video, we can have a val over here, a stable identifier. We're going to call it ord. I'm going to assign it to ordering. So now we can import ord. Now, and because we have that, because we importing ord, we can go to all the places where we do .hashcode and we can just remove them. Right, so over here, because we're importing ord, so we can use this symbol over here so we can compare them. So over here in contains and add and remove those 6 places, we're just going to remove it like that. Notice that I didn't save the file. Today we're compiling with our brains. Okay, so now let's say that our trees, they have this ordering. So where we're going to inject it? Well, as I said, at the moment of the creation. So that we have two kinds of tree. We have the empty and we have the non-empty. I just scrolled down real quick. Okay, so it's actually the first time that we're doing this, but a case class or regular classes, it can have a second parameter list. We only did this with functions so far. It's very, very similar. So it's basically partial functions behind it. If you want to construct only the first part, then you need to use a factory on non-empty, and you can't use new non-empty. In fact, let me show this to you. So I'm just gonna do Scala over here, and I'm gonna do case class person. Let's say name string, and age comes in as the second parameter. Okay, so we can say, okay, give me the first part, which is no, give me the second part, which is a function that takes an integer and constructs a person, and we can just say, okay, it's a person with Bob. Okay, so now you have this function where you can pass in 20, and what you're gonna get is Bob was, was the age of 20. Okay, you actually don't see that the age is 20. Hold up, can we do a 0.age? I believe that we can't. Okay, so we actually have to go to person and do something like this. Hold up, we need to do, let's say that this is A. Okay, and we're gonna have def age equals A. Okay, like this. So now if we go, can we do F20? Hold up, F20. No, we can't. We have to create it first, like this, like that. Okay, so let's do F20. Okay, res3.age. Okay, it's 20. So as you can see, but you can't do this, right? So you can't just do new person over here, right? You can't do that. Okay. So let's go back to this thing. Okay, so we need to add one over here. So we're gonna go and say override val ordering, which is an ordering of element. And now we're also gonna notice that we need to change this object from an object to a class. So this is also gonna be a final case class, and we're gonna have an empty parameter list over here. And the second one is going to be override val ordering of element, like this. Now technically we would need to go to nothing and also make sure that an ordering comes in so that we can construct an empty instance over here, but I don't really know how to do that now. So for now I'm just gonna do this. I'm gonna throw an exception like this. Now ideally we would also try to prevent our users to pass in a different ordering every time a non-empty or empty is constructed. So in the past we had case classes like completely private. In this case of the tree, we actually don't want to do that. Now the second option would be to make the constructor private, but that's not going to work for us, and because we want a pattern match on that. And I just don't want to go and create the extractor completely manually and the factory completely manually, because it's just gonna steal a bunch of time. This is just an education project, but ideally you wouldn't want people to just go and at any point in time and create a non-empty with a different ordering or create an empty with a different ordering. The only way to create tree should be able to it should be by going through the factory, right? So through this apply and through this empty. Let's go and continue with our changes. Because we have empty as a class now, we need to find the places where we use it. So we're gonna go over here. Okay, so we have over here case empty. Let's do like that. Let's find another instance of empty. It's over here. Let's do like that. Let's find another one. It's over here. Okay, in this case we're actually using it, so we can actually bind it. So we can do empty at empty like that. Okay, the next one is going to be over here like that. Let's see if we have it somewhere else over here like that. So that's just going to be empty element like that. What else? Empty over here. What else? Okay, I believe this is it. Okay, so the next thing that we're going to do is we're actually going to go and inject ordering at all of these places where we're constructing non-empty and so on. So we're going to go up and we're going to see, okay, non-empty, blah, blah, blah. We're not constructing anything over here. Fold, not constructing it over here. Add. Okay, so over here when we're constructing a non-empty, we need to make sure that we're passing in the ordering. And also notice that the copy method that is being generated by the case class, it also has a second parameter list now, so we can go and pass ordering over here. And by the way, we could make it implicit at the injection point, and then we wouldn't need to do this whole thing, but it's only 5 places, I believe, so it's all good. I prefer to have it like this. Okay, ordering, and over here ordering. So just a few seconds ago, I jumped to the factory, and this factory obviously doesn't know anything about ordering. So what we need to do is we need to copy that. We need to go down. We need to paste it somewhere over here, and we need to say that what we're constructing over here is a tree copy. And let's see. So we're gonna call it with custom ordering, and we're gonna take let's say that over here. Gonna open the brace over here like that, and over here we're not gonna call empty. We're also gonna call with custom ordering, and we're gonna pass it the ordering like this. And this is gonna look pretty much the same as this one over here, right? But it's not gonna be a final override. It's just gonna be a final def. It's gonna be called with custom ordering, and it's going to get an instance of ordering like this, ordering of element like this, and it's creating a tree copy of elements. Okay, how is it going to do this? Well, it's going to go over here and it's going to create an empty like that, and it's going to pass in the ordering. Now notice that all of this time I still haven't saved the file, and we're not trying to compile anything, but let's pretend like everything works, and we're going to go over here and we're going to create a main method. Okay, we're going to say it extends app. Okay, and we're going to do a first tree. Actually, let's copy my favorite hyphens. If I go to Fibonacci, for example, I can just copy that. Okay, so let's just do this. Let me scroll down a little bit. In fact, we actually don't need all of this space. Okay, so let's do that. Let's do that like this. Okay, so we're gonna have a first tree, which is gonna be a tree copy of int, which is going to be a tree copy dot with custom ordering 1 2 3 1 2 3 like this. Okay, and we're going to pass it the ordering of int. Okay, and we're going to create a second tree. Let me actually go over here. This is a second tree, and this is going to be the same tree, but the ordering is going to be in reverse, right? So it's going to be ordering reverse. Okay, so what we're going to do is we're going to print out the first tree dot rendered. Going to do the same thing with the second tree over here, and we're also going to compare them. Okay, so I'm gonna have first tree equals second tree. Okay, so this is gonna be the first time we're gonna try to actually compile and actually run it. Okay, so we're gonna say run main homegrown.collections main like this. So this is not gonna compile. Okay, it's only 2 errors, which means that it doesn't compile for the reasons that I wanted it not to compile. Okay, this is too much of copy pasting. So with custom rendering over here, you can't have a val inside of a def like that. Okay, so we have 12 of them. Element not found. Okay, where did that happen? 1 to 6. Let's go over here. 1 to 6 was custom ordering. Okay, I forgot to say that an element comes in like that. All right. Empty does not take type parameters. Okay, over here. Element. So in the end, it's not going to compile, but I wanted to not compile for the right reasons. And I believe that we actually arrived at the point. Let me scroll up. All right. So it says value less than or equals is not a member of type parameter super. Type mismatch, found ordering of element, but what it wanted an ordering of super. Same thing over here, same thing over here, same thing over here, same thing over here, here, and here. So we have these 8 errors, and we're going to realize right now that this whole ordering thing is not going to work with covariance. So if you go to the add method, for example, over here. Now, as I already said, it's not a good idea to inject an ordering over here, but even if we tried, we wouldn't be able to. I mean, we sort of would be able to, right? So we need to do something like this. We need to say, okay, give us an ordering of super, right? So this is it will look something like this, okay? But there's no way that we can ensure that this instance that is being passed in is going to be the same one, or that it's going to behave the same. Okay, we cannot express it in the type system that we need a new instance of exactly the same kind of ordering, but for a different type, right? We can't say that we already have an ordering for an element. Give us now an ordering for super that it's going to behave exactly the same way. There is no way to ensure this, to encode this into the type system. No way that I know, or no way to do it in a quick introduction video, in a quick educational video. I mean, okay. So what we're going to do instead is we're going to comment this entire tree copy out. Okay, let's just comment it out, the whole thing, like that. Come on, like that. Okay, let's go back to running the tests. So what are we going to do? We need to make a tough choice. We have, in my opinion, only two options. The first one is let's have the tree copy completely separate from the rest of the library. Let's not make it extend foldable and foldable factory and all of that stuff. Let's have it completely separate. And in fact, if this was a production level library, this is probably what I would go with. But this is not a production level library. This is an educational video. So instead, we're going to go with option B, which is going through the entire library and get rid of the entire covariance because I never liked it in the first place. All right, so we have a pretty heavy refactoring, but it shouldn't actually take too long. So let me switch to compiling and let's just go. Okay, so I'm gonna uncomment the sidebar so that you sometimes see in which file we're in. So the first one is at the top of the hierarchy, we're gonna have foldable. All right, so everywhere where we say plus element over here, we're just going to say element instead. And everywhere we have super element, we're just going to remove all of them. And everywhere we say super, we're just going to say element like this. Now we're going to save the file because we have multiple files, so I'm forced to saving the file. I'm just going to make sure real quick that all the compilation errors are not coming from foldable. So one is in tree, one is in set, and another one is in factory, and so on and so on and so on. Okay, so there's actually nothing in foldable, I believe. So the foldable is actually fine. The next one that we're going to go to is going to be factory. Okay, so we have a plus E over here. So let's just remove the plus. Do we have super anywhere? Not really. We're pretty much done. Okay, let's go to oh yeah, we also need to remove nothing because of the whole covariance thing. Okay, so let me just remove nothing like this, and the only abstract method is going to be empty, so it needs to be abstract. Okay, like this, and we need to do the same thing in factory 2. Let's go to factory 2. There's one plus over here. There's nothing over here, okay, because the key was invariant anyway. All right, so let's go to foldable factory. Okay, hold on, this one, foldable factory. Let's do the same thing. Everywhere we say plus element, we're just gonna say element. Everywhere we have super element, we're just gonna remove it from everywhere. Everywhere we say super, we're just gonna say element like this. Okay, let's go to foldable factory 2, do the same thing, plus value, it's just going to be value. Everywhere we have super value, going to do that. Everywhere we have super value, just going to do value like this. All right, so now we're having problems with sets and trees, so let's go to set. Same thing, not a plus element anymore. This is just element. All right, everywhere we have super element, it's all gone. Everywhere we have super, we have element. Now we just need to go down over here, and we need to make sure that we're overriding empty, which once an element gets in a set of element, and it uses an empty tree of element like this. All right, so the next thing is going to be tree like this, same thing, plus element goes into element, and super element is going to become so much code for basically no reason. All right, element like this, let's go down, and it also has nothing. It's going to be actually empty with element, and it's going to produce a tree of element like this. So now we have to do the same trick as before. We need to do final case class empty over here. All right, we don't have ordering yet, so we just have this. So this is just going to construct an empty like that. Let me press enter over here like this. Okay, so now we pretty much need to go through all the pattern matching and do the same trick. So case empty like this, and over here like that, and over here like that, and over here like that, and let's see what else. Same thing over here, empty element, oops, element, and what else? Empty over here. Okay, I believe this is it. So now we need to go to set, and we need to do the same thing. So every time we say tree.empty, it's going to be that, and over here also Sublime. Okay, So let's see, empty, t.empty like that, empty. Okay, I believe that this is it. The only thing that is left is somewhere in map. Plus element is set. What are we? 320, 320, 120. Do we still have pluses somewhere? I thought we didn't. Foldable factory doesn't have pluses. Foldable, whoops. Foldable doesn't have pluses. Let's go to tree again. Hold up. Tree 120. Oh, I said nothing over here. Element. There we go. All right. So empty does not take parameters. Yes, it does. It's right here. Element like this. Okay. All right. Only one error in map. Okay, we forgot to touch the map. Map, same thing. Plus value. It's gonna become value. And do we have anything that smells like super? Yes, we do. Over here, remove that. Super value just turns into value. And okay, tree.empty align 65. Same thing over here, tree.empty. Anything else? No, it compiles. All right, so now we just need to continue with our tests. So if we go to our tests like that, we have a bunch of stuff, mostly in the set suite. So let me open the set suite. We don't need the sidebar anymore. I'm going to collapse it like this. All right, so the problem is that everywhere we have nothing, dot nothing, we need to replace it with empty. All right, so we're going to have to say dot empty, and in many cases we will actually have to also specify the type parameter. So we're going to go from the bottom, so we're going to go to line 671. So we're going to go and say that these are strings over here, not strong, string like this. Okay, so we're down to 42, 666 like this. All right, so this is the one with the variance, so we're just going to remove it. We don't really need it. Okay. So we're down to 41, 636. Same thing over here. We need a string over here, right? Okay, 39, 517. Same thing over here. Let's say that this is string. In fact, we would actually say nothing over here, I believe, but it doesn't really matter. Okay, so 513, same thing. Okay, string like that. All right, down to 37, 455. Okay, set that empty. Let's make a string. I didn't do it in the beginning, like I didn't replace all of them, all of the set that nothing with set that empty string, because we don't need it everywhere. Okay, but maybe I should have. Okay, 245. Let's do string over here. Let's string like this, and over here as well, string. Let's see. Okay, 35. 241, which is over here. All right, this is the variance again. We have the employees and stuff. Let's get rid of it. Okay, 33, 218. All right, so over here we need to say it over here. 29. Okay, 202. Same here. Which one does it not like? This one or this one? Oh, let's specify it in both. I don't really care. As I said, this is, everything over here is on a different branch anyway. So, okay, 1 and 5. All right, so this one is just over here. We just went from 28 to 16 because, it's in a central point like this. Same here. What is it? Intersection, blah, blah, blah. Oh, these are probably 161, 160, probably these ones. String, I don't know if we need it over here, but we probably do. String like this, probably these are the ones as well. It's not very good string. Typing is hard, huh? All right, 158. Okay, so it's basically all of these. So let's go here and say string. Let's go here and do the same. String here and here. String. All right, so we're down to 10, 150. Okay, this one is the one with the variance. Let's get rid of it. All right, 1 to 9. We're almost done here. Union. Okay, so this is the one was here. Let's do string. Okay, 4, 371. 371. What? There's nothing on 3. Oh, it's map suite. All right, map suite. 371. All right, so this is the variance. Let's get rid of it. Okay. All right, 335. Okay, this is a weird one. So let's do string, string, and in fact we need tuples over here, like this and like that. RS, random string, and I believe now it should be fine. Everything compiles and everything should still be green because we never, we removed the test for the variance and everything else was a very, very mechanical transformation. So it should all be good. All right, so everything is fine now. So let's go to our tree copy. Right, let's comment it back in and let's remove the variance the same as we did for the others. So we're going to have element over here, and every time we have super element we're just going to remove that, and we're going to, every time we say super, we're just going to say element, and let's see where we are. All right, it looks like we did something wrong with the empty case. Empty element, oh yeah, here, element, like this. All right, so there's something wrong with the import. What's wrong with the import? It's not a member of type parameter element. What? Oh, I typed in org over here. It should be ord. Jesus. All right. So, method empty and trade factory, blah, blah, blah is not defined. Okay, let's go down. Oh yeah, we have it over here. So it's empty and element comes in, right? And the tree copy comes out of element. And we also need to create it over here. All right, it's empty. And what are we going to do here? Well, this is the first time where we're going to be explicit about the fact that our trees are going to be hash trees, at least if we construct them like this. So we're going to go to ordering by, and we're just going to do hash code like this. Okay. All right, everything is green again. So now for the first time, we should be able to run our main method, which is over there. And there we go. So one of the trees was constructed in this way and the other tree was constructed in that way. So it seems like all that is left to do is to switch to running the tests, and remove our old trees. So we're going to go to tree, we're just going to comment it all out. In fact, I'm just going to remove the entire file, delete file like this. Okay, and we're going to go to tree copy and rename tree copy to tree, and we also can rename the file to tree, rename tree. Okay, all of the tests are still green, everything is still fine, seemingly. All right, now everything seems fine. Let me collapse the sidebar, okay? Because we don't actually have any of the tests that do anything with ordering, okay? So I'm not gonna go and create them, so we're just gonna go back to running our main, and I'm gonna show you a few things. So the first thing that we're gonna do is, let me remove those print lines over here, and we're just gonna print out something else. So we're gonna go to the second tree, for example. Second tree. Okay, so we're gonna go and we're gonna say remove 1, remove 2, remove 3. Right, so now it's empty. Okay, this is very important. We're gonna map it to identity. We're gonna map, we're mapping the empty tree to an identity, right? And then we're gonna add back in 1, we're gonna add back in 2, and we're gonna add back in 3, and we're gonna do dot rendered. And now we're going to do the same thing, but the first time I'm going to do it without the map. And let's see what's going to come out. Different trees came out. What happened? It looks like we lost our ordering because we're mapping to identity. How did this happen? Well, if you go to map, we should jump to foldable factory. Right, so what it did was it was constructing, it said, okay, if I'm working with an empty tree, which is what I did, this is why I went and I removed all the elements. So I wanted to make sure that we're working with an empty tree. In fact, let me just have that, hold on, tree, foldable factory, close, tabs to the right. Okay, so this is all that we need. In fact, maybe actually let's do that. Okay, so I removed everything. I'm calling map. Map calls fold, and fold says, okay, if everything, if all the hell breaks loose, if we're dealing with an empty thing, then we're just going to go to factory.empty. And factory.empty is ending up being over here, right? So this is how we lose our ordering. Our ordering is being converted into the ordering of hash code. Now, I told you already in the previous video, which was the crash course about ordering, that there's an entire branch of mathematics dedicated to ordering. Things was programming is hard. Math is even harder. So only because ordering seems so intuitive, actually many things can get broken. This is exactly why we're doing this on a different branch, and this is exactly why I'm also going to link down. I'm also going to link the video down in the description below about Haskell, where Edward Kmett is talking exactly about this topic. He's actually talking about type-class coherence, but he brings up exactly this example where you have a set and you want to have it in ordering, and what can you do, what you can't do. Now, obviously, we can just continue with this, and we can create a different kind of a foldable factory where we'll inject ordering, and then it will be aware of the fact that the ordering is there. Also, soon we're gonna start working on on stacks. Remember, we have a very initial version of stacks, but we need to actually go and finish them. And stacks, they have an intrinsic notion of ordering, right? So maybe we would put ordering in there somehow, and inside of the foldable factory, the ordering would be optional, and then for the stacks, it would be always a sum, and for all the others, it would be none or something. We could go like this like crazy. But I don't want to go into this even in more depth. In fact, I even considered not making this video, but then I realized that you might benefit from it actually. So I said, we're just gonna go to a different branch. We're gonna play around with it, just gonna throw it all out, and you guys can benefit from that. Now, I want to mention one more thing. Actually, let me remove that other one. Okay, so we're gonna go to why did it jump over there? Actually, let's just close. Okay, so in that talk, Edward Kmett is also talking about the thing called Hedge union. And Hedge union is an algorithm to merge two sets in a very efficient way. So in there, divide and conquer is used, and two sets are being traversed at the same time. And the new one is being assembled with only essentially like one traversal, so to say. And we haven't, we don't really care about performance here because this is an educational video. I said it in the very beginning of this playlist, which was like almost a year ago. Okay, so our union actually has in a complexity of that dot size multiplied with a logarithm of this dot size, right? So this is an m log n, right? So this is the complexity. Okay, so we don't really care about this, but it turns out that even though we don't care about this, and even though our tests are green, our union is still doing the wrong thing. Let me go to the main method. I'm actually going to show this to you. So we're going to go back to our original example, okay, over here. So we're going to go and we're going to say over here, we're going to say print out first tree. I'm going to say union second tree, okay. We're going to say the rendered over here. Going to do it the other way around. Second tree here. First tree over here. Let's see. What is wrong with me today? I can't type rendered like this. As you can see, not the same thing comes out. And union has a contract. It has to be commutative, right? So it shouldn't matter which way you do it, right? So the different thing comes out. In fact, it's actually so bad that if we switch to sets, right? So our sets, they don't have custom ordering. So we could just let's do that. Let's copy that. Let's go into set. Let's go to the bottom and inject these over here, right? We're just gonna switch tree to set. Let me double check that real quick. So gonna go with custom ordering. Okay, over here we're constructing an empty. Can we do that? No, that's not what we need to do. We need to construct. We need to go to apply like this. This is how we construct a set, I believe. Yes, let's see. No, obviously not. We need to go here and say tree dot with custom ordering like this. Okay, so this works now. So if you go back to our example over here and we switch from trees to sets, right? So if I'm just going to do set over here, we need to go into the tree and do the rendered. We're going to see that the same thing is happening, which means our sets actually have duplicates now, right? So if I copy that, if I just print it out, this one and this one and this one as well, and then I scroll down, our sets have duplicates now all of a sudden, right? This is completely broken. All right, so essentially I made this video just to show you that even when things seem very intuitive, they still can be very hard. Programming is really hard. Math is also not easy. And as I already mentioned in the previous video, math has an entire dedicated branch, even multiple branches dedicated to ordering. This is not simple. In fact, I believe that there is actually not even a straightforward solution to this topic. In my research, all I found was that the only sort of way to solve this is to have an ordering on sort of the modular level. So something like the cake pattern, where you have like, you know, the entire collections library in this cake, and inside of this cake there's only one notion of ordering, right? So then when you create union knows that these sets, they have the same ordering, right? But this is obviously like way too much. We're not going to go into that. So what I'm going to do is I'm going to keep even the main method. So I'm just going to go over here, and I'm going to add all the files. Whoops, not a comma, dot, like this. I'm going to do git commit -am. That's going to be video 26 ordering, like this. So I'm going to push it, and we actually technically don't need -- all because we're on the branch that we're pushing. Okay, so let's just do that. All right, my key. Okay, there we go. What does it say? Create a pull request for ordering. It's my branch. Should all be fine. Let's go check it out. Okay. Wow, that's interesting. I have my SSH key. Is it like a new thing? Weird. In any case, I'm gonna leave it like this. I'm gonna figure this out later because I don't want to merge it. Like, it didn't happen with red black trees. Maybe this is a new feature or something. So we have like 3 branches over here, and if you go to commits, we only see the commits on the master branch, so we don't see the video 26. Also, why is my avatar not being rendered? It's being rendered over here. It's being rendered on the hover. Doesn't matter. Okay, so if we switch to the branch ordering, then we see the video 26, so it went from 25 to 26. If we go back to red black trees over here, then we see that we stopped at video 11, right? So if you go to master, then if you go down, we're going to see that 11 is not there. We have 10, and then we go back to straight to 12. All right, so I'm going to figure this out a bit later. I don't know what's going on with that pull request. That's all I got for you today. It's been Vlad, devinsider.com. Don't forget to like this video. Don't mess with the ordering, and most importantly, take care.